Picture yourself aboard a spacecraft capable of exceeding the speed of light, hurtling directly toward the Andromeda Galaxy. Sounds impossible, right? But not for us, at least not today. In just 10 minutes, we're about to accomplish what would take modern spacecraft millions of years. So, what's waiting for us in our galactic neighbor? What similarities does Andromeda share with the Milky Way, and where do they differ? One thing is certain: beyond our solar system lies not only a vast sea of stars and awe-inspiring cosmic formations, but perhaps even the answers to life beyond Earth and the origins of the universe itself. Stick with us until the end, because this is one cosmic adventure you won't want to miss. Although much has changed since ancient times, one thing remains the same: our curiosity about the night sky. Thousands of years ago, just like today, humans gazed upward in wonder, questioning the nature of the luminous patterns above. Back in 964 AD, Persian astronomer Abd al-Rahman al-Sufi observed a faint, misty patch in the constellation Andromeda, which he poetically named the Little Cloud. But what was this mysterious object? At the time, its true identity was far from clear. For centuries, the true nature of a certain mysterious structure remained unknown. It wasn't until October 6, 1923, that a breakthrough finally came. Up until then, this object had been believed to be just a nebula within our Milky Way, a reasonable assumption, given that the Milky Way was once thought to be the only galaxy in existence. That all changed thanks to Edwin Hubble. Using the newly developed telescope at California's Mount Wilson Observatory, the ambitious astronomer closely examined a faint spot of light known as Messier 31. Through his observations, Hubble identified Cepheid variable stars, stellar markers that allowed him to calculate distances with remarkable accuracy. His findings revealed that these stars were far beyond the Milky Way. This revelation completely transformed our understanding of the universe. Around a century ago, Hubble demonstrated that Andromeda was not a gas cloud within our galaxy but a separate galaxy altogether, what was then referred to as an island universe. In that moment, the scale of the cosmos expanded unimaginably, and the Milky Way was no longer alone, but merely one galaxy among billions. As if this groundbreaking shift in our understanding of the cosmos weren't astonishing enough, Hubble soon made another incredible discovery: nearly all galaxies are moving away from one another. This led to the conclusion that the universe is expanding, implying it began with the Big Bang. Clearly, the study of the Andromeda Galaxy played a pivotal role in shaping modern cosmology. And today, we're turning our attention back to it, equipped with a spacecraft that would have exceeded even Edwin Hubble's most ambitious dreams. But is faster-than-light travel possible? From the outset, we're faced with a major challenge. Though Andromeda is our closest galactic neighbor, it still lies an incredible 2.5 million light-years away. Even a theoretical spacecraft traveling at 99.9% the speed of light would need more than 2 million years to reach it. And according to Einstein's special theory of relativity, no object with mass can reach, let alone surpass, the speed of light. However, what if we didn't need to break the laws of physics, but instead found a way to bend them? Surprisingly, theoretical physicists have already proposed concepts that could make this possible without violating Einstein's principles. The most famous of these is the Alcubierre warp drive, a theoretical propulsion system that doesn't move a ship through space, but moves space around the ship. The idea is that space behind the vessel expands while space in front of it contracts, effectively allowing the spacecraft to ride a wave through space without exceeding light speed. Another intriguing possibility involves wormholes, hypothetical tunnels through spacetime that could connect two distant locations instantly. These shortcuts, if they exist, might one day make intergalactic travel a reality. On paper, wormholes could theoretically serve as stable, usable portals through space, assuming, of course, we could discover or engineer exotic matter with negative energy to keep them open. Luckily, for the purposes of this video, we've managed to do exactly that, at least in our imaginations. Our futuristic spacecraft brings together two advanced concepts. It generates a stable artificial wormhole sustained by a field of negative energy, and it's also equipped with a warp drive. Is this all science fiction? Absolutely, but it's grounded in real physics, at least at the conceptual level. And now, the journey begins. Destination, the Andromeda Galaxy. We step aboard the ship and take one final glance at Earth. The engines engage, no dramatic jolt or explosive noise, just a subtle ripple in reality itself. Outside the window, the stars begin to stretch and twist, as if space and time are folding around us. Within seconds, we're beyond the solar system. Planets flash by in an instant, Neptune shrinks into a distant dot, the Kuiper belt slips away, and even the Oort cloud, that icy, distant shell marking the edge of our solar neighborhood, blurs into obscurity. We've left our home system behind, venturing into regions no spacecraft has ever reached. The voyage to the Andromeda Galaxy is officially underway. But first, we must traverse the vast, silent ocean of intergalactic space. At first glance, this region might appear like a vast, empty ocean in space, but in truth, it's brimming with cosmic mysteries. Our journey begins by moving through the halo of the Milky Way, a vast, spherical shell made up of dark matter and ancient stars. Within this region lie globular clusters like Messier 92 and Messier 13, both over 12 billion years old, serving as remnants from the universe's earliest times. Some of the stars here are so ancient they contain almost no metals. These are known as population 2 stars, born in the universe's infancy. Next, we enter the intergalactic medium. Though stars are rare in this region, it's filled with matter, mostly in the form of ionized gas. Scientists have found through observations and simulations that this gas forms immense, thread-like structures known as filaments, stretching across the entire universe. As we travel through these cosmic strands, we pass through frigid zones with temperatures nearing absolute zero, around -273.5 degrees Celsius. Yet, scattered among them are pockets of hot gas, remnants of powerful supernova explosions. Occasionally, we encounter a solitary star, an intergalactic wanderer ejected from its home galaxy during violent collisions, now drifting alone in the vastness of space. Nearing the end of our journey, just before reaching the Andromeda Galaxy, we pass by the Triangulum Galaxy, also called Messier 33. While this voyage is imaginary for now, it might one day become a reality as our understanding and exploration of the cosmos continue to grow. Experts are now debating the possibility of a future collision involving the spiral galaxy Triangulum, the Milky Way, and the Andromeda Galaxy. Despite having only about 2% of the Milky Way's mass, the Triangulum Galaxy is still a significant member of the local group. It hosts NGC 604, a massive star-forming region stretching about 1,300 light-years across, making it one of the largest known in any of our neighboring galaxies. Then, we reach Andromeda itself. Once a faint smudge in the night sky to ancient observers, it now dominates our view as a vast spiral structure. This transformation is no accident. After analyzing more than 3,000 infrared images from the Spitzer Space Telescope, a team of American researchers concluded that Andromeda contains an astonishing 1 trillion stars, far more than the Milky Way's estimated 100 to 400 billion. Andromeda also contains notable features like ML2 and G1, the brightest globular cluster in the entire local group. Interestingly, some scientists believe G1 may not be a true cluster but instead the dense core of a dwarf galaxy currently being absorbed by Andromeda. Both Andromeda and the Milky Way are classified as spiral galaxies, though the Milky Way is specifically a barred spiral. In Andromeda's case, most studies indicate it has 2 primary spiral arms extending from a central bar, sweeping across its enormous structure. Within the spiral arms of galaxies, we find regions where new stars are born, so-called H2 regions, and remarkable structures like NGC 206, one of the largest known open star clusters. These areas provide a vivid glimpse into the life cycle of stars, how they form, evolve, and eventually die.